This is my third video lesson for Unit 8. In this lesson, we'll be discussing other gas laws. Go to page 13 in the class packet. These are the gas laws from the previous PowerPoint. If we combine them, we'll get the relationship V is proportional to N times T over P, or V equals X times NT over P. X is a constant. Assuming we have 1 mole of gas at STP, what is the value of X? We can move X by itself on one side, assuming 1 mole of gas at STP, P is 1 atmosphere, V is 22.4 because 1 mole of gas takes up 22.4 liters of space at STP, there's 1 mole, and the temperature is 273 Kelvin at STP. X is equal to 0.0821. This is known as the gas constant. Learning target. At the end of the lesson, I'll be able to calculate the property of a gas using the ideal gas law, Graham's law, and Dalton's partial pressure. Homework B number 3, which be a Junipod based off this lesson. PV equals nRT is the ideal gas equation. P is pressure, V is volume, N is mole, T is temperature. R is the universal gas constant. Depending on what units you're given, here are different variations of the universal gas constant. Keep in mind, PV equals nRT equation is not on the Regents exam. Let's look at some questions. The first one, a tank of hydrogen gas has a volume of 22.9 liters and holds 14 moles of gas at 12 degrees Celsius. What is the pressure of the gas in atmosphere? The first step is to write the equation, PV equals nRT. Make sure you convert the degrees Celsius into Kelvin because you cannot use degrees Celsius for gas laws. Next, you plug in the known information and solve for P. Notice I use 0.082 for R because we're given liters and atmosphere in the question. We get P is equal to 14 atmosphere, and that's the answer. For question 2, what volume in milliliters at STP will be occupied by 0.0035 mole of methane? We will use P equals nRT. We're given N, which is 0.035. STP tells us the pressure and the temperature, 1 atmosphere and 273 Kelvin. We can plug it in and solve for V. Since we have liters, we have to multiply by 1,000 to get milliliters. So the final answer is 78 milliliters. Now try to do the rest of the practice yourself. Pause the video and resume when it's completed. Here are the answers. This is the real gas law equation. Notice that we have 2 extra variables, A and B. What were the assumptions of an ideal gas in the kinetic molecular theory? The 2 assumptions were the gas particles have no volume and intramolecular forces, so A addresses the intramolecular forces of the particle, and B addresses the volume of the particle. Here are the table of the constants for each of the substances. The next gas law that we're going to cover is Graham's law of effusion and diffusion. Diffusion is when particles move from high to low concentration. Here's a GIF to show that. Effusion is the rate at which particles are escaping through a hole. Here's a GIF showing the gas particles escaping through a bottle. Here's a diagram in your packet showing diffusion and effusion. Graham's law seeks to answer why do all gases cause the same pressure? At the same temperature, the kinetic energy of different gases are the same. Why is that? Because temperature is the average kinetic energy. Kinetic energy is 1/2 mv squared. M is mass, v is velocity. If the masses of the gases are different, what does it mean by the speed of those gas particles? It means that the small particles will move faster, the large particles move slower, so that the kinetic energy is the same. What factors might affect the fusion rate? There's 2 factors, the temperature and the mass. From the kinetic energy equation, we can derive Graham's law equation. The rate of effusion of A over the rate of fusion of B is equal to the square root of molar mass of B over the square root of molar mass of A. Question 1. How does the rate of effusion of hydrogen compare to the rate of effusion of oxygen? A will be hydrogen and B will be oxygen. We have to look up the molar mass of H2 and O2. O2 is 32 and H2 is 2. We plug into the equation. It will be the square root of 32 over the square root of 2, and we get 4. This means that hydrogen molecules effuse 4 times faster than those of oxygen molecules. Smaller molecules and atoms will diffuse or effuse faster than larger ones. Learning check number 1. At STP, which of the following gases would diffuse most rapidly? Pause the video and resume as completed. So you have to look for the smallest molar mass, and that would be NH3. Answer is choice 2. Learning check number 2. Which of the following gases will have the slowest rate of diffusion when all the gases are held at the same temperature and pressure? Pause the video and resume as completed. So we're looking for the biggest molar mass. That would be choice 4, CO2. The last gas law that we're going to cover is Dalton partial pressure. In a mixture of non-reacting gases, the total pressure exerted is equal to the sum of the partial pressures of the individual gases. Here we have gas A, gas B, and gas C. Each of these gases have their own individual pressure. If we were to combine all these gases into one container, this would be a mixture of gas A, gas B, and gas C. The total pressure in the mixture will be the sum of the individual pressures. The pressure of A, the pressure of B, the pressure of C, you add them up, that would be the total pressure of this mixture. Learning check number 3. What is the pressure of a mixture of CO2, SO2, and H2O gases if each of the gas has a partial pressure of 50 kilopascal? Pause the video and resume once completed. Since each gas is 50 kilopascal, the sum will be 50 times 3 or 150. Choice 3. So the total pressure of a mixture is the sum of the individual gases. Each partial pressure of the individual gas is equal to the mole fraction of that gas times the pressure of the total. Mole fraction is the moles of the substance over the total moles in the mixture. Let's look at an example. A sealed container has 1 mole of helium and 2 moles of nitrogen at 30 degrees Celsius. When the total pressure of the mixture is 60 kilopascal, what is the partial pressure of nitrogen? We know the partial pressure of nitrogen plus the partial pressure of helium gives us the total pressure of the mixture. However, we do not know the pressure of helium. We do know that the partial pressure of nitrogen is equal to the total pressure times the mole fraction of nitrogen. The total pressure is 60 kilopascal. The total moles will be 1 mole of helium plus 2 moles of nitrogen, gives us 3 moles altogether for the mixture. The mole fraction of nitrogen will be 2 moles over 3. So the partial pressure of nitrogen is 60 times 2/3, which is 40 kilopascal. Choice 3. You can also solve for the partial pressure of helium. It will be 60 times 1/3, which is 20 kilopascal. The sum of the partial pressures should give you the total pressure of the mixture. 40 plus 20 gives us 60. Question 1. If 4 moles of oxygen gas, 3 moles of hydrogen gas, and 1 mole of nitrogen gas are combined in a closed container at standard pressure, what is the partial pressure exerted by the hydrogen gas? We know the partial pressure of hydrogen is equal to the total pressure times the mole fraction of hydrogen. From the question, we know that total pressure is 1 atmosphere because it's standard pressure. The total moles is going to be 8. 4 plus 3 plus 1 is 8. So the mole fraction of hydrogen is 3 over 8. 3 over 8 times 1 gives us 0.375 atmosphere. So the answer is choice 4. Question 2. A mixture of gases have a total pressure of 200 kilopascal. The mixture contains 8 moles of nitrogen and 2 moles of oxygen gas. What pressure is exerted by the oxygen gas molecules? We know that the partial pressure of oxygen is equal to the total pressure times the mole fraction of oxygen. The total pressure is 200 kilopascal. From the question, the total moles will be 10. The mole fraction of oxygen will be 2 over 10, so the partial pressure of oxygen will be 200 times 2 over 10, which is 40. The answer is choice 2. Question 3. A gas sample consisting of 2 moles of hydrogen and 1 mole of oxygen is collected over water at 29 degrees Celsius and 75 kilopascal. What is the partial pressure of the hydrogen in the sample? We know the partial pressure of hydrogen is equal to the total pressure times the mole fraction of hydrogen. The total pressure is 75 kilopascal from the question. The total moles is 2 plus 1, which is 3 moles. The mole fraction of hydrogen will be 2/3, so the partial pressure of hydrogen will be 75 times 2/3, which is 50 kilopascal, so the answer is choice 2. So this concludes the video lesson for today. Remember to do the Junipod homework.